Welcome to Chemistry with Caroline. In this video, we're going to look at the competition between substitution and elimination reactions for a tertiary alkyl halide. So this is the most hindered system we'll see. We have three alkyl groups coming off of the carbon with the leaving group on it. And so that hindrance is definitely going to impact what type of reaction we see. And then the other factor is what our nucleophile/base looks like. So one molecule can act as a nucleophile or a base, and so we can characterize that molecule as a weak base or a strong base, and that can help us distinguish which reaction pathway is going to be the major product. When you have a weak base, you tend to see substitution reactions, particularly on a crowded system. So with a weak base, you're definitely going to see a substitution reaction. Because of the tertiary system and the stability of the carbocation, you're going to see an SN1 reaction. It's too hindered for SN2. And the tertiary carbocation is stable, relatively speaking at least. So we'll just see SN1 reactions there, no SN2. It's too crowded for an SN2 type reaction. You can see a minor amount of E1 product in a combination of a weak base and a tertiary alkyl halide, especially if you have heat added to the mixture, but E1 is always going to be sort of a minor product in these type of reactions. With a hindered system and a strong base, you're going to see an elimination reaction. That strong base can go to the periphery of the molecule and pull off a proton as opposed to going all the way into an electrophilic carbon. There's a lot less steric hindrance there. And again, you're going to see an E2 type elimination. So in this example, we look at a tertiary alkyl bromide. We can either see SN1, which is probably going to be the major, if not the only product that's observed in many cases. The only way that we could know that E1 happened is if we look at our product mixture through spectroscopy, say a GCMS or an NMR or something. For both types of mechanisms, the first step for this particular system would be the departure of the leaving group. So the leaving group leaves, and that gives me a carbocation. And for the SN1, you would have that weak base behave as a nucleophile, and that would come in and give me my substitution product. Or for the E1 type reaction, the carbon with my carbocation on it is the alpha carbon, so then any of the neighboring carbons would be beta carbons. They're all equivalent to one another. This is a symmetrical molecule, so I could draw it off of whichever one. And so in this case, the weak base would behave as a base, and it would pluck a proton off of the beta position, and those electrons would fold down to make a double bond, and that would give me my E1 type product. For a tertiary system, when you have a strong base, you'll see an E2 type elimination. So again, this carbon with the leaving group on it is the alpha carbon, so any next door neighbors would be beta. Because all of these methyl groups are coming off of the same carbon atom, they're in an identical environment. It's symmetrical on that end. And so they're all labeled beta. You could draw the mechanism by plucking the proton off of any of those. And so this base, the oxygen that's negatively charged, is going to use a lone pair to grab a proton off of one of the beta positions. These electrons will fold down to make the double bond, and this bromine will leave all at the same time. So that's a concerted E2 type elimination, and it gives you the same product of an E1 elimination, but the mechanism is different, and we can know that because of the presence of this strong base. So that's been a look at competition between substitution and elimination reactions for a tertiary system. If you found this video helpful, please like, subscribe, and share with your friends. Thanks.